Okay, good morning. Looks like it'll be almost private sessions. Let's see. Filters, resonance circuits. And 2.1. Okay, let's start with this. What does this remind you of? Loudspeaker? Hmm? I mean, if this is, you're college students, if this is not familiar, you need to like get out a bit more. Nah, I'm just kidding. Of course, it's a loudspeaker, right? This is a speaker box with three-way driver. So each individual speaker in here is known as a driver. Okay. Yeah, the big one. Anyone know what the big one is called? Not a subwoofer, just a woofer. Sub would be even lower frequencies than woofers. Produces a loud thumping noises. This is the tweeter, and this is for mid-range vocals. Anyone have a subwoofer in their car? I had two when I was a grad student. Cheap ones. I installed it myself, but I was rocking it. Yes. Okay, there is a purpose to this. I mean, the example in the illustration. So we have a loudspeaker box. This is known as a three-way loudspeaker because there are three individual drivers in there. Each of these drivers, the mid-range, the tweeter, and the woofer, has a specific purpose. Okay. Audio frequencies, right? Normal human range is between 20 hertz and 20 kilohertz. More likely, it's 100 hertz up to probably about 15, 16 kilohertz. Okay. And depending on the frequency, each frequency, of course, will have a wavelength. And depending on the frequency, the sound reproduction by each speaker is specific to the range of those frequencies. If it's low frequencies, you need a large speaker, large physical dimensions. And that is reproduced by the woofer, which is the low frequencies, okay? Which is loud thumping noises, explosions that you see in movies, the deep bass that you hear in audio songs, okay, in music. Tweeter is for high frequencies, high frequency reproduction, and mid-range is for vocals. So as I said, each one of them has a specific purpose because they can accurately reproduce the sound for each frequencies, okay? So these are known as three-way speakers. Most speakers would be like two-way speakers. You would have like one small tweeter to reproduce high frequencies and one large one to produce low frequencies. Even like small cube speakers will have two individual drivers inside it. The speakers that you see installed here in the classroom, more likely than not, are two-way speakers. There'd probably be like a woofer in there and there's a tweeter in there. So if you look at the back of this cabinet, you would see something like this. These are known as banana plugs. If you're taking the lab, these are exactly the same. Okay, you can insert a banana cable directly into these terminals. You can also wire up or screw in individual wires and tighten the screws. Anyway, so at the back of this, you have only one cable going in. Each speaker has a positive and negative terminal. So if you have one individual cable coming in, how is it split in three? And that happens using the magic of a band pass filter. There is, in every speaker box, there is a filter circuit. Every speaker box is a filter circuit. Remember, I said RC and RL low pass filters. Depending on which component you take the output from, you can obtain either a low pass filter or a high pass filter in the exact same circuit. So inside the speaker box, if you open up the back panel, which is basically just, it'll be like two screws on either side. If you open it up, you will see that the wires inside the box actually go to a circuit. That circuit would have like a heavy inductive coil, might have a few large capacitors, and it will have a few resistors. This network will actually split the incoming signal into 3 individual outputs. Okay. Split into 3 individual outputs. One of them will go to the mid-range, one of them will go to the low frequencies, one of them go to the high frequencies. The circuit is known as a crossover network. Crossover network. Okay. And every speaker box will have a filter like this inside it. The cheapest speakers that you can find will have a resistor and a capacitor soldered directly on top of the speaker itself. Like, I kid you not, I've seen like really cheap speakers that would have like a resistor without any wires. It's directly mounted on top of the speaker itself. You have like a resistor, and the other end of the resistor goes to a capacitor, and the capacitor is connected to the other end of the speakers. And you have like a filter circuit right on top without any circuit board, without any wiring. So if you have like a cheap speaker, lying around somewhere, open it up, smash it open, and take a look. There'll always be a simple RC. RC filters are cheap. Components are like, it wouldn't cost more than $1. So if you're making this in bulk, it'll cost a few cents. Crossover networks like these are expensive. So depending on the make and model of this loudspeaker, these crossover networks could run into like, tens of hundreds of dollars. Again, because these would be like heavy inductive coils. They would do a good job of filtering out. You need a high quality inductor, which would not result in a loss of signals. So these are all passive filters because there is no active amplification going in. Meaning if the signal comes in, you want your resistors, capacitors, and inductors to not degrade the output much. There might be some signal loss, but not a lot. Anyway, so this is a crossover network. The technical term for this network would be like a band pass filter. Okay, a band pass filter, which could give you an output for low frequencies, high frequencies, and a mid-range band. Okay, and that is the application of what we are going to see for a resonant circuit. Okay, resonant circuit. So resonance is a phenomena that occurs in nature. You have mechanical resonance, right? You've heard, perhaps of old wooden bridges or structures falling apart during a windstorm or a naturally occurring events where the vibrations of the structure resulted in its collapse. One of the most common ones, you say, oh, there was a singer who was singing such a high volume or loud noise that the glass shattered. Never seen it happen in real life, but that's a very real thing that is possible. That is possible. That is due to mechanical resonance. Electrical resonance takes place due to the presence of two opposing energy storage devices. Meaning if you have an inductor and a capacitor together in a circuit, there is a phenomenon that is known as electrical resonance that could occur. And that results in voltages and currents that are larger than the source appearing in the circuit. It's a possibility. Not always, but it's a possibility. But the way we are going to look at is they are resonant circuits, and the application of these resonant circuits is as a band pass filter. So I will explain a little bit of the theory behind it, and then I will go over the equations. Okay. So resonant circuits are of two kinds, series and parallel, depending on how we connect the components. Here you see it's all connected in series. So you ignore the output terminals. There's no component connected to the output terminals. So R, L, and C are all connected in series. And then you have parallel resonance, where all of them are connected in parallel. Okay. Now, if it's series resonance, let me redraw it down here. R, L, and C, and you apply the input. So let's say this is L, R, and C. Let's say the inductor was not present in the circuit. There was no inductor in the circuit. It was just R and C. And if you take the output across the capacitor, what kind of output would you expect? So V in is a range of frequencies, let's say 20 hertz to 20 kilohertz. And you have different bands, and depending on the values of the components, if you take the output across the capacitor in a RC circuit, what kind of filter? That's the first filter we saw in this chapter. Low pass. Capacitor is open at low frequencies, meaning you would get an output. And if you take the output across the resistor in a RC circuit, you'd get a high pass filter, right? But let's take a look at RL. If there was no capacitor present and you applied a signal to an RL circuit and you take the output across the inductor, you would expect to have a high pass response. And we see that in the previous circuits. So output across the inductor, it's a high pass circuit. Output across the capacitor would be a low pass. Oh, that's RL. So RC across the capacitor, you have a low pass circuit. So a series resonant circuit, if you combine everything together, you can have a high pass output, low pass output, and depending, of course, on the values of these components, you can have a certain band of frequencies that are allowed to pass through in the middle. And I will explain how and why. So let's start with a graphical illustration. Your frequency here, you have V out on the y-axis. Low pass filter, what does it look like? Oh, I do the high pass one first. All right, this is the low pass filter. Okay. And this would be the high pass. So high pass, low pass. And right in the middle, if I take this as 0.707, 0.707 times V in, it intersects both at their respective cutoff frequencies or break frequencies, right? So this is the cutoff frequency or the break frequency for the high pass filter. And this is the cutoff frequency for the low pass filter. Let's take a pause while you think on this. Let me know if you have any questions. Do the graphs make sense? We have two graphs, both representing two individual circuits. But if we combine them together, you have a high pass filter and you have a low pass filter. And if you take the cutoff frequencies for each one, there is a certain band of frequencies in the middle that is passed through. Questions? Any questions? Yeah. We can just do a frequency response. Yes. Yeah. We would you can do it as an oscilloscope if you just want to use. So the question being asked is, how can we test the performance? So the performance of a filter can simply be, can be done with a variety of ways. Oscilloscope, of course, is an option. And this is something that if students are taking the lab, in the lab for this week, the resonant circuits lab for lab 7 is something where you will test the performance of a resonant circuit, and you'd obtain a chart that looks like this. So it looks like a bell curve. So you have the high pass filter that has a cutoff frequency, you have low pass filter that has a cutoff frequencies. So that means if we design our filter, our resonant circuit with the components, we can design a band pass filtering output for specific frequencies. Okay. If we choose the component value such, we can allow a narrow band or we can allow a very wide band. Okay. So it just depends on the application. Most applications require a very narrow band of frequencies to pass through. For example, if you tune your radio station to 101.7 megahertz, it should only allow that radio frequency to enter into your radio device. It should block out everything else. Okay, so it's a very narrow band of frequencies. Okay. On the other hand, if you ever used a graphic equalizer, whether a manual one or an electronic one, and you look at the different bands, it will state that each individual slider or each individual slider volume control will allow a certain band of frequencies. Those are much wider. Okay. So depending on how much it is, depending on what the application is and how many sliders there are. So you have like 5 band equalizers, you have 10 band equalizers, you have 15, 20, 30 band equalizers. So the more you have, the more control you have. The smallest ones, you have 2, bass and treble, right? Low frequencies and high frequencies. Those are filters. So as I was saying, you have 2 filters, they are combined together. The one on the left is for the high pass filtering option. The one on the right is for the low pass filtering. But technically, the value of the one on the right is higher. So it's sometimes referred to as FH, and this is FL, just because the value is higher. But it corresponds to the low pass filtering output. Remember, frequency is increasing to the right. So the value on the right is higher than the value on the left. So FL and FH. But the filtering is actually the opposite. Does that make sense to everyone? Hence, we get a band pass filter. Let me ask you this. You have 2 frequencies, right? You have the high pass here, and you have the low pass here, and you have a band of frequencies that are allowed to pass through. What if you switch the 2 frequencies? What kind of filter would you get? So you have, what I'm asking for online students is that what if you switch the LPF and HPF FBs? You would get something like this. FBs are now switched. you have a high pass filter FB that's on the right and the low pass that's on the left. So it becomes a band reject or band stop. Band reject or band stop filter. Okay. Like there are certain band of frequencies we don't want coming in, we reject those and everything else comes in. So again, designing with the values of the components, you can change how it looks. So that's the actual application, but let's actually look at what happens at resonance and when it happens, or how it occurs and when it occurs. It occurs due to the energy storage properties of the inductor and the capacitor. Okay. In the positive half cycle, energy flows into an inductor, and in the negative half cycle, the energy flows out. Capacitor is the exact opposite of an inductor. So for a capacitor, in a positive half cycle, the energy flows out, and in the negative half cycle, the energy flows in. So when you have both capacitors and inductors in the same circuit, the energy comes out of one component and goes into the other, and then bounces back and forth between the two, vice versa. This is a very important concept for our next chapter, which is AC power, also for lab 8. Okay. So when you have two energy storage devices, one inductor, one capacitor, which are opposites of each other, the energy is localized and bounces between the two. And for that reason, voltages and currents that are larger than the source could appear in the circuit. Because if you apply a 10-volt source and the inductor or capacitor stores 5 volts or 10 volts, now you have 10 more volts coming in the next half cycle. If there's 5 volts stored in there, you now have 15 volts. That's a very simplistic explanation, but that's how it comes about. Okay, energy is stored in the system, and so then it bounces back and forth, and then voltages larger could appear. Now you have a range of frequencies that is applied to the circuit. At one particular frequency, at one particular input frequency, what happens is that the impedance of the inductor and the capacitor are exactly the same. The magnitude is the same, but the phase is exactly opposite. This is a series circuit, right? So the current is the same. Current is the same. That means the reference point for the inductor and the capacitor is exactly the same. So if that is the same, then the impedance of the inductor and capacitor is out of phase by exactly 180 degrees. And so when you add them up, something like this. Remember I talked about noise cancellation? You add up two signals of the exact same frequency and the exact same magnitude, but 180 degrees out of phase, they will cancel each other out. And that is what happens. So at one single particular frequency, the impedance of the capacitor and the inductor are exactly equal in magnitude, but opposite in phase. So the total equivalent impedance of the entire circuit is simply the resistor, ZR. ZR. Okay. And the output will go to maximum. And that occurs at one single frequency known as resonant frequency F0, and that is given by the values of the components L and C. L and C. And this is the same for both series as well as resonance, as well as parallel resonance circuits. Okay, no difference. I'll explain quickly how and why. At resonant frequency, ZL plus ZC is equal to 0. Hence, total ZEQ is simply equal to R. Okay. There are a few other equations, but there are other concepts I'd like to point out. So we have two frequencies in there, right? Two frequencies in there. FL and FH. The difference between the two is known as the bandwidth. Bandwidth of that filter, or the bandwidth of the resonant circuit. Okay. Bandwidth. There is also a quantity that we use to describe the quality of the filter. And the quality basically describes how narrow the band is. Okay, how narrow the band is. Most applications require a band pass filter to be very narrow, as I stated, right? If you're tuning it to a particular radio station, you want just that one single frequency going in, everything else should be rejected. So it's a very, very narrow band. Sometimes it might be if you tune the radio station exactly between two frequencies, you might hear both radio stations coming in. Have you ever had that effect observed? And the reason is because if it's in the middle, it's filtering a little bit of one station, it's filtering a little bit of the other station. And so both signals are coming in because they're not completely blocked out. That's the reason why it happens. Okay, so quality for a series resonant circuit is labeled as QS. QS, quality of a series resonant circuit, is given in terms of the components. And in terms of the frequency and the bandwidth, it is simply the resonant frequency divided by the bandwidth. The narrower the band, the higher the quality. The wider the band, the lower the quality. Okay. But again, that quality, it depends on the application. Okay. In general. If the quality of a resonant circuit is higher, let's say typically higher than 5 or 6, then we can assume that the curve or the graph is approximately symmetrical around that resonant frequency. And then F0 is about halfway between FH and FL. Okay. That is only if the quality is much higher. So if QS is higher than, let's say, 5, then we can say it's symmetrical and it's located halfway between. Now the equations are exactly the same for parallel resonance. So I'll go to the equations first. F0 is exactly the same. Bandwidth is also exactly the same. Quality in terms of the resonant frequency and bandwidth is also the same. The only difference is QP is different. It's flipped because it's now connected in parallel. Everything else remains the same. Okay. Now, the way it works here is like this. You have ZEQ, it's in parallel. You have R. You have 1 over R plus, and I'm going to separate this out so it makes it easier, ZL plus 1 over ZC, right? If I just solve the other two, ZL plus ZC in parallel, what do we get? we get ZL times ZC and ZL plus ZC. And we take the reciprocal of just this right here at resonant frequency. So this would be ZL plus ZC, which goes to 0 at F0. Okay, because they are connected in parallel, this time the cumulative effect of ZL and ZC is that ZL plus ZC goes to infinity. Okay, so the effect of ZL and ZC in parallel is that it's infinity. Combined effect. Okay, but the result is again the same. The only component that is left in the circuit effectively is simply the resistor. And so total ZEQ that is seen by the source is simply the resistor itself. IC and IL would be equal to 0 because nothing would go down that path. So this is the critical difference between the two. The result is exactly the same, but the difference is this. In a series resonant circuit, ZL and ZC combine to give you an effective impedance of 0 ohms. And in a parallel circuit, ZL and ZC combine to give you infinite impedance. But the cumulative effect of both is that it's purely resistive. And because it's purely resistive, you have maximum output in the circuit at resonant frequency. All other values, either the inductor or the capacitor will offer some impedance, and so the output drops. And you get a graph that looks like a bandpass filter. All right, any questions? Again, if you have the opportunity, open up one of the back panels of this loudspeakers and see if you can look at a crossover network. Okay, let's go into Bode plots, last topic. All right, Bode plots, again, developed by an engineer working for Bell Labs, H.W. Bode, basically is a plot of the magnitude of the transfer function in decibels versus frequency in a log scale. Both are compressed scales. You take a very large range of values, both of the x-axis and the y-axis, and you compress it down so you can plot them all on a same standard chart. And the reason is, of course, in engineering, we deal with a wide range of values, from the very, very small to the very, very big. When you're talking about frequencies, frequencies can run into like hundreds of thousands of hertz, right? We run into gigahertz and terahertz range. So if you want to plot this, we need like a chart paper that's like miles long on a linear scale. But on a log scale, you can plot it all on a single graph paper. Okay. So what we do is we take our y-axis and we compress it, and you take your x-axis and you compress it. And I will explain how we do that. Let's look at frequencies first. Okay. Frequencies are plotted on the y-axis, and we plot frequencies using the log scale. Okay. Now we define a log to the base 10 of two frequencies, or ratio of two frequencies, as one single decade. So a decade is basically a change of 10:1. 10:1. If you start at 1 hertz and you go up to 10 hertz, then the range of frequencies between 10 and 1 is 1 decade. If you start at 10 hertz and go up to 100, the ratio is again 1:10. So 10 hertz to 100 hertz is also 1 decade of frequencies. Okay, 1 decade of frequencies. Octave, again, this is just for informational purposes. Octave is basically a 2-to-1 change in the ratio of frequencies. So it's log of the ratio of two frequencies to the base 2. The base 2. Okay, so as an example here, 100 or 500, the difference between 500 and 100 is 2, hence it's 1 octave. So when we plot this on the x-axis, our scales or the log on the x-axis is in log, it's not in linear. How many of you have ever used this kind of chart before? Okay, if you're engineers, you would have used this, or you may use this in the future. It is not just for electrical engineering, it's for all engineering and scientific applications. Okay, this is what is known as a semi-log graph or a semi-log chart. There are also log-log, where both axes, x and y, are in log scale. Here, for Bode plots specifically, the x-axis in the log scale, y-axis is linear, but the y-axis plots either the voltage or the transfer function. And before we plot it, we compress it using a new unit, which is what we'll see in the next slide. So on the x-axis of a log scale or a log chart, the distance between the 2 points, 2 divisions, is in the log range. Okay, hence a log scale. So the way it works is there is no 0 on a log scale, right? If you take log of 1, log of 2, log of 3, log of 4, there is no 0. So you start with 1, 2, 3, 4, 5, 6, 7, 8, 9 divisions. And there's a multiplier for every single division. So let's say for the first division, our multiplier is 10 raised to 0. For a linear scale, you add it up. 1 plus 2 plus 3 plus 4. For a log scale, you multiply. So it's 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3, 10 raised to 4. If I was plotting frequencies, 10 raised to 0 is 1. So my first division would be 1 hertz. Then 2, 3, 4, 5, 6, 7, 8, 9 hertz. And then the multiplier changes. When my new division starts up, it's 1 into 10 raised to 1. So after 9, you go to 1 again, and 1 into 10 raised to 1 gives me 10 hertz. Second division is 2, becomes 20. So it's 10, 20, 30, 40, 50, 60, till 100 hertz. Then it's 200, 300, 400, up to 1,000. Then 2,000, 3,000, 4,000, all the way up to 10,000, 10 kilohertz. Then 20,000, 30,000, 40,000, and 100,000, 100 kilohertz. You can have 100,000 data points in one small chart, which is virtually impossible in a linear scale. So you're compressing by using the log of your data. Does that make sense? Let's take a pause. Let me know if you have any questions. Okay. All right. Then let's look at the y-axis. Y-axis, we are plotting. What are we plotting? We are plotting our transfer function. Okay. Transfer function is the ratio of voltages. You can often also plot voltages using this exact same definition. So this was during the early days of telephony, where engineers at Bell Labs were trying to work, not just Bell Labs, telephone engineers were working to quantify the power loss that occurred in telephone transmission lines. Okay, so you had a transmitting frequency at one end, transmitting power at one end, and then power loss during the line, and then you obtain some power at the other end. Because of the wide range of variations, they came up with a new unit. And who did they name this unit after? Yeah, of Bell Labs. And they said, we'll take the log of the ratio of the two powers, input power, output power, P2 over P1 to the base 10 log, you get Bell. To make the unit even smaller, they broke it up into 10 different parts. So you get 10 bells. That's where you get deci. Remember chapter 1, unit prefixes? Deci, centi, milli, micro. Deci is 1/10, centi is 100, and milli is 1,000. 1 over 1,000, 1 over 100. And so they came up with a new unit called decibels, or dBs for short. dB is 10 times log of P2 to P1, meaning 2 powers, the ratio of 2 powers to the base 10. Okay? The ratio of 2 powers. Power is V squared over R. When you plug that into this equation, your decibels in volts comes out to be 20 times V2 over V1. A transfer function is a ratio of voltages, V2 over V1, V out over V in. Transfer function in dBs, hence, can be described as 20 times log of the magnitude of h of f. So you're taking your h of f, wide range of values, and you compress it by taking the log. And hence, when you plot it here, you don't need to use a log scale because your data is already compressed. Hence, we plot it on a linear scale. X-axis is compressed on the chart. So you use a log scale, but the y-axis, the data itself is compressed before you plot it on the chart. Hence, we simply use a linear scale. And hence a semi-log chart or a semi-log graph. Does that make sense? Okay. There was a question a student asked. Let's take a pause. Let me know if you have any questions before I move on. Any questions? Okay. So there was a question a student asked me about how we obtain the magnitude of the transfer functions, specifically these. Okay. So I'll just go over that a little bit. It also ties into the reason why we take 1.707 of V out or 0.707 of the transfer function. So I'll do, I have about 6-7 minutes left. So transfer function for a low pass filter is h of f is 1 over 1 plus j f over fb, right? If I wish to find the magnitude, it will be magnitude of 1 divided by magnitude of the denominator. Okay. Again, goes back to the fundamentals of finding magnitudes of a right angle triangle. Of a complex number. Complex number can be represented trigonometry as a right angle triangle. So if you have a plus jb is a complex number, the magnitude of a plus jb is given by the hypotenuse, Pythagoras theorem. So a square plus b square. And hence, if you try to find the magnitude of h of f, obviously the numerator magnitude of 1 simply remains 1, but magnitude of 1, the denominator, would be 1 square plus f over fb square and square root. That's where it comes from. And then, of course, phase angle theta is tan inverse or arctan. Arctan or tan inverse is the same thing. Tan inverse of y over x or b over a. Let's use, since I'm b over a. Okay, b over a. So if I was trying to find the phase angle or the phase of the transfer function, it will be 1 phase angle 0 divided by the angle for 1 plus j f over fb. Okay. An angle for 1 over j f over fb would be tan inverse of f over fb divided by 1, which would be tan inverse of f over fb. Does that make sense? Right? Tan inverse of f over fb. Now, this simply becomes 0 minus tan inverse of f over fb. And that's the derivation. Hence, it becomes minus tan inverse of f over fb. Same thing you can derive for the high pass filter. Okay, high pass filter has an extra term in the numerator, which is jf over fb. So when you apply the same concepts, you would obtain 90 degrees at the top in the numerator minus arctan of f over fb. Also, look at this magnitude. What do you have? Denominator is root of 1 plus f over fb. At f input frequency equals to fb, what do you get? 1. Hence, this becomes root of 2, which is magnitude of h of f becomes 1 over root 2 at the input frequency equals to fb. And guess what value is 1 over root 2? 0.07071, I think. And hence we use 0.707. Okay. So 0.707, the magnitude of the transfer function V out drops to 70%. Okay. V out is, sorry, H of F is a ratio of voltages. When you plug in power, power is V square. That root 2, 1 over root 2, or power 1 over root 2 squared becomes 1 over 2. Hence, the power drops to half at F over FB, hence half power frequencies. Okay, half power frequencies. All right. Sorry to rush through this. It's just, there's always a lot of explanations and derivations that we can do, but we just don't have enough time to get into everything. That's just the reality of things. So we'll end class here today. That is the end of chapter 6. On Friday, we'll look at AC power. Again, some of the concepts that I talked about will apply to AC power also. Okay. If you have any questions, I have a few more minutes before we begin next class. I will be in my office later this afternoon. Stop by if you have any questions. Get started on the homework. Resonant circuits, there's one more homework. All right.